All right, I'm going to review. Hopefully you guys will have come up with the proper things, but just in terms of a quick sine chart, again, our sine charts are just another x-axis. All right, so there's my x-axis. I'm going to mark critical points. Again, critical points, and we're going to put some definitions up when I get back, but critical points are where either f prime equals 0, meaning I have horizontal tangents, okay, or f prime doesn't exist, meaning that I have funny business. And funny business are cusps, corners, peaks, vertical tangents, and discontinuities. Okay, so that's what I'm going to mark on my sine chart. So just an x-axis at x equals 0, I have a horizontal tangent, so I'm going to mark that on my sine chart. I'm going to put information about my function, and I'm looking at my function every time, so I'm going to be filling in this part first. I always put in words about my function. So my function starts out decreasing and switches to increasing. Okay, so then I put in information about f prime. The information I take about f prime is whether or not it is positive or negative. So when I have a horizontal tangent, f prime has a value of 0. Okay, when f is decreasing, f prime is negative. When f is increasing, f prime is positive. Okay, what we talked about in yesterday's video is that if I am dealing strictly with a parabola, and I know this is exactly a parabola, that the derivative will be linear. Okay, I don't know the slope of it, but my derivative should look something like that. So where the value 0 is happening where the function has a horizontal tangent. So the derivative has a value of 0 where the function has a horizontal tangent. It's negative, meaning below the x-axis. It's positive, meaning above the x-axis. Moving on to this one, okay, hopefully you guys see that you have another horizontal tangent at x equals 0. So at x equals 0, f prime has a value of 0. Okay, again, words about f. And the words that I choose are increasing, decreasing. So my function increases before that horizontal tangent and increases afterwards, which means the derivative is going to be positive and then 0 and then positive. So positive meaning above the x-axis, down to a value of 0, and then positive again. Okay, so it looks a lot like a parabola. For C, we can actually be really specific about the derivative here because I have a linear function. Remember that you guys spent 7th grade, 8th grade, 9th grade, 10th grade, and a lot of 11th grade talking about the slopes of lines, and they were always constants. Okay, so just over here, I have a slope of 1. Over here, I have a slope of -1. It doesn't matter where you pick. My slope is always -1 on this side, always +1 on this side. What's happening at the origin? Well, it's a critical point because I have a corner and my derivative doesn't exist there. Oh, I'm going to make this really hard with the sine chart. All right, I'll do it on a separate sheet of paper. So my derivative is actually equal to -1 over here and equal to +1 here because those are my slopes. All right, so let me just graph that for us. So this is what our sine chart looked like, that at 0, my derivative didn't exist. Before 0, my derivative had a value of -1. After 0, a value of +1. A value of -1 is a constant value of -1. At 0, my derivative doesn't exist. A value of +1 is a constant value of +1. My derivative of 0 doesn't exist. Okay, so this is the graph for f prime when f of x is equal to absolute value of x. Okay, back to this. All right, sine x, I've got a lot of horizontal tangents here. It's very exciting. So I've got my horizontal tangent here and here and here and here. So I'm going to have on my sine chart, I have a 0 for my derivative. Every time my function has a horizontal tangent, they should be equally spaced, but my scale kind of sucks a little bit. My graph starts out increasing and then switches to decreasing up until this point, right? And then I'm going to increase up to pi over 2, and then decrease again to 3 pi over 2, and then increase again at the end, which means my derivative is going to go, every time my function increases, the derivative is positive. Okay, every time my function decreases, my derivative is negative. Now, I have to separate myself and ignore this for a second, and I'm just looking at, I need to graph a function who's positive then 0, then negative then 0, then positive then 0, then negative then 0, then positive again. So let me just take care of the zeros. So my zeros are going to occur where I have a horizontal tangent. If f prime has a value of 0, then f prime is on the x-axis. Okay, so my zeros on F prime match the horizontal tangents on F. Do you guys see that? All right, now these are kind of anchor points that can allow us to figure out what's going on here. So I'm just gonna look in between these two zeros. My derivative is supposed to be negative, which means it should lie below the x-axis. Okay, so I've got to go down below, but then back up to that next zero. And then on this interval from negative pi over 2 pi over 2, my derivative is positive. So I got to go 0 and then above the axis to be positive and then back to that 0. So it's going to kind of look like that. Okay, you don't know how tall it goes or how low they go. If yours went taller or lower, it's fine. We'll get into specifics later. We're talking about basic shape. Again, your graphs don't need to be perfect, but they do need to be accurate. From pi over 2 to 3 pi over 2, my derivative is supposed to be negative, meaning below the x-axis. So I have to get it from this 0, go below, and then get back to that 0. So it's going to look like that. And then we can kind of assume what the ends of the graph look like, right? And that matches positive, positive, above, above. All right, that's what the graph looks like. So the derivative of sine x appears to be, think about it if you haven't already, but it appears to be cosine of x. Okay, now for cosine. Lots of horizontal tangents again. Right, I've got one here, and here, and here, and here, and one last one there. So at negative 2 pi, I've got a horizontal tangent. At negative pi, I've got a horizontal tangent. At 0, I've got a horizontal tangent. At pi, I've got a horizontal tangent. At 2 pi, I've got a horizontal tangent. So my derivative has a lot of zeros, which is actually really, really helpful because they act as anchor points. So a 0 there, a 0 there, a 0 here, one over here, and one last one here. My function is decreasing on this first interval, and then switches to increasing, and then goes back to decreasing, and then goes back to increasing, and my graph kind of only exists here. Where a function is decreasing, its derivative is negative. Where a function is increasing, its derivative is positive. So I'm going to have to graph from this 0 negative values, which means below the x-axis, but back to that 0. So below and then back to the 0. Again, you don't know how low it dips. We're not concerned with that, just the fact that it has a 0, then goes below the x-axis, and then back to 0. All right, we will figure out how low it dips in the next section. Right now, we are not going to worry about that. And when I say the next section, I mean like the next chapter after this test, so don't even stress about it right now. On this interval from negative pi to 0, my derivative is supposed to be positive. So I have to get from 0, be above the x-axis, and then back to a 0, so it's going to look kind of like that. On the next interval, 0, negative 0, you guys are kind of getting the hang of this now, I hope, and then 0, positive 0. All right. The derivative of cosine is looking like it's a graph of negative sine. Something to think about. This tangent graph is a ton of fun, all right? Just so that you guys recognize that if my function is undefined, then the derivative is also undefined. So where f doesn't exist, which is at all those vertical asymptotes, f prime also doesn't exist. If f has a vertical asymptote, f prime is going to also have vertical asymptotes. Okay, I'll blow up discontinuities. If you look at each of these intervals, my function's always increasing. So increase, increase, increase. There's no zero slopes. It's one of the things I was telling you that y equals x cubed does get horizontal at the origin. Tangent does not ever get horizontal there. Now, I know from experience, and you could ask a computer or a calculator what the slope is exactly here, but you're not supposed to know, okay? We just recognize that my slopes start out a very steep positive. Remove that, a very steep positive, and then they get less positive, and then they go back to more and more and more positive. So my slopes on these intervals need to go from, I'll write that down, very positive slopes to less positive and back to very positive, okay? If I think about where very positive values are located, that means high, less positive means come down, and get very positive again means go back up, right? As far as values go, it'd be above the x-axis, very positive, less positive, very positive. I don't know how low it's going to dip, how close to the x-axis it's going to go. Well, I know, but you don't. But the point is that it doesn't hit the x-axis because the slope is never 0 because I never have a horizontal tangent line. So each of these intervals, I'm going to go from a very positive slope, less positive, and then get back to very positive again. very positive, right? You can see that, very positive, less positive, very positive. So very positive means values that are high, less positive dip down, and very positive again. They're all gonna look like that. They should all come down as low as each other. I'm kind of watching through my phone, so my graph isn't perfect, but you guys get the drift. Okay, hard to do a sign chart for that one because there's not a lot to put on there other than, you know, a bunch of positive values. We need to be more specific. For G, with that secant graph, hopefully you guys graphed that secant function properly. If not, this is what it looks like. Fix your graph, pause, and come back to me if your secant graph wasn't accurate in the first place. But let's make a sign chart. Now, there's a lot going on this sign chart, and I don't really have enough room for it. Maybe, let me see. Okay. So I have both horizontal tangents and vertical asymptotes. So every place I have a vertical asymptote, which is here, 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 at all the multiples of pi over 2. Well, not all the multiples, but pi over 2 plus pi k. I know how you love when I talk like that. My derivatives are going to not exist, right? If I have vertical asymptotes on my function, then I have vertical asymptotes on my derivative. And that's just because if you look at any time you approach a vertical asymptote, you get super duper steep. It doesn't matter if you're going steep, which direction you're going steep in, but steep slopes, big slopes are going to go off in towards infinity or negative infinity. We could talk more about that, but okay. And then I also have all these horizontal tangents. So at 0, I have a horizontal tangent. At pi, I have a horizontal tangent. At, what is that? 2 pi, I have a horizontal tangent. At negative pi over, what is that? Negative pi, I have a horizontal tangent. At negative 2 pi, I have a horizontal tangent. And then there's like a lot going on here. So my first graph, my first piece, I started here and I ended at those horizontal tangents. So my first piece starts out increasing, and then this piece is also increasing, and then I'm decreasing. And then the next piece is decreasing, and then it switches to increasing. And then I'm increasing, and then I'm decreasing, and then I'm decreasing. All right, so now every time I'm increasing, my derivative is positive. This is such a mess, isn't it? And then every time I'm decreasing, my derivative is negative. Okay, so now I gotta make sense of this. So with the zeros, I'm gonna throw on there right away. So if I have a horizontal tangent, my derivative is 0. Horizontal tangent right here, derivative is 0. Horizontal tangent, derivative is 0. Horizontal tangent, derivative is 0. Horizontal tangent, derivative is 0. All the asymptotes that are on f are gonna be asymptotes on f prime. So I need to go from this 0 value, and then if you guys look at this, my slopes start out at 0, right, at the bottom of that little U-shaped piece, and then they're gonna get more positive, more positive. You see how steep my pencil tangent line is going? So extremely positive slopes. So extremely positive values are like way up there. So I'm just gonna go for these extremely positive values in the way that I would approach a vertical asymptote. Okay. My next section, this little interval here, my slopes also start out extremely positive, and then they get less positive until they're 0. Extremely positive numbers are way up here, and then they're going to get less positive. On the other side of this, my slopes go small negatives to bigger negatives to bigger negatives to bigger negatives, so I'm just going to bottom out this way. All right, same thing here, extremely negative slopes, less negative until I get to that 0. So extremely negative until I get to that 0. And then my slopes are gonna get extremely positive. And at this point, hopefully I recognize a pattern. Extremely positive slopes start up high, and then I'm gonna go for extremely negative slopes down there. Here on this last piece, my slopes start extremely negative and they progressively get less negative. So extremely negative means way down below, and less negative gets in there. If I went through that too quickly for you, please rewatch it, okay? It might make more sense the second time. H is another problem where a sign chart is not super helpful. There are no critical points on this function, on any exponential for that matter. Okay, my function is increasing, so the derivative is positive. That's not at all helpful, so we need to be more specific by looking at slopes of our tangent line. Okay, so my slopes start out close to 0 here, and they get increasingly positive, and at the end, the whole idea of exponential functions is they shoot up. So I'm eventually going to have extremely vertical, well, I shouldn't say vertical, but extremely steep positive slopes. Okay, so my values start close to 0, and then they gradually get very positive. So if you think about on an x-axis, over here, okay, close to 0 means close to the x-axis, and then get very positive means just go up. Okay, as far as how steep this is relative to, this is what the derivative looks like for, which one is that, h? Okay, it's, as far as how steep that is relative to the original function, you're not going to know right now, and just like I said, the general shape is what matters. So your derivative should look pretty much just like the function, okay? All right, moving on to I, same issue. There's no critical points. There's no horizontal tangents. There's no funny business. There's no cusps, corners, peaks, vertical tangents, or discontinuities. Just to worthy of speaking about, my graph only exists to the right of the y-axis. Your derivative also better only exists to the right of the y-axis. If you graph derivative in either quadrants 2 or 3, you're in trouble because there's no function there to talk about the slope of its derivative. Here, the conversation is just another ambiguous one like we had for h, where my slopes start out extremely positive, get less positive and less positive until they're going to eventually get closer and closer and closer to 0. Okay, so f prime has to go from very extremely positive closer to 0. So very positive values, that's way high up. So very positive slopes, and then come down to have slopes closer to 0. All right, that's what my derivative should look like for that one. All right, we're almost done here. So over here, I've got a few critical points for this one. Let me get some more paper in here. So if I'm going to make a sign chart on here, I just have one critical point. It's at x equals 0, and it's because I have a a blow up discontinuity there. My derivative is not going to exist. And just remember that if a function has a vertical asymptote, then its derivative will also have a vertical asymptote. So I could see my function decreases and decreases. Again, this is not super duper helpful, which means the derivative is always negative. Derivative always negative, meaning I'm going to graph it below the x-axis, but we're going to need to be more specific. On this side, my slopes start out close to 0 and get more negative, more until they're getting extremely negative. So on this side, I need to graph close to 0 and then go down to extremely negative. So close to 0, wait a second, that's near the x-axis. Extremely negative means fall. So my derivative is going to look a lot like my function. In terms of how is it different, we don't care, basic shape, okay? We'll get to the details of how accurate it has to be later on once we learn the shortcuts for derivatives. Right now we're talking about basic shape, locations, proper x-intercepts, proper discontinuities kind of stuff. On this side, my slopes start out extremely negative, and then they get less negative, and closer to 0. So extremely negative. And I have a lot of students who write this stuff out every time because it's super helpful. If that's helpful to you, then do it. So extremely negative means start way down and get closer and closer to 0 means come back up. So we're going to start way down on this one and come closer and closer to 0. All right. There you go. All right, my graph of radical x. All right, here's another reason, because I told you my favorite thing is slope. This is why I wanted these graphs to be accurate. I start out with a vertical tangent line. Here's another one where my function is only defined where x is greater than 0. Okay, so you better not have any derivative graphed in either quadrants 2 or 3, because if the function doesn't exist, we cannot talk about the slope of its tangent line. So you only can draw from the side in quadrants 1 and 4 when x is greater than 0 to the right of the y-axis. All right, so I hope that you notice that my derivative doesn't exist at x equals 0 because I do have that vertical tangent line that I was so picky about you drawing. So my slopes at a vertical tangent line, those are really, really, really positive slopes, and then they're eventually getting less and less positive. Okay, so very positive, extremely positive, down to, they're eventually going to get close to 0. Okay, so very positive means start way up high, and close to 0 means come down towards the x-axis. So I'm going to start way up high and then come close to 0 towards the x-axis, and that's basically what my derivative looks like. It has asymptotic behavior there. Okay. And finally, my semicircle. So for my semicircle, we talked about, do my same chart down here again. At the ends of the semicircle, okay, I have vertical tangents, right? So my derivative is not going to exist there. So my derivative is gonna DNE or UND, whatever you want to talk about, how you want to call it. And then I also have a horizontal tangent up when x is 0, so I'm gonna put that on there too. Okay, so horizontal tangents are great. I can lock that in right away. My derivative has an intercept at the origin because my function has a horizontal tangent when x equals 0. My function starts out increasing and ends decreasing, which means my derivative is going to go from positive to negative. A couple more details here. The graph does not exist beyond negative a on this side or positive a on this side. So if your graph extends beyond the circle, something is wrong. You cannot graph a derivative if you don't have function there. And then let's just talk about this. My slopes are starting out ridiculously positive and then getting less positive, less positive, less positive, less positive until they hit 0. So on this side where I said the slopes have to be positive, meaning they're above the x-axis, they're super positive, and then they get less positive, and then they get closer to 0. Well, they actually hit the 0, right? Okay, so super positive values, those are really, really, really high values. I'm actually gonna have vertical asymptotes here on my derivative. So super positive values, very positive slope values, less positive, down to 0. Okay, on this side, my slopes start out at 0, and then they get negative, more negative, more negative, more negative, ridiculously negative. Okay, so they start out at 0 on this side for these negative values. They start out at 0, and then they got to be small negative, and then they get super negative. Okay, so 0 is here, small negatives means below, super negative, I'm going to have another asymptotic behavior in here. Okay, and so it's going to pop down like that. Okay, and that's what the derivative looks like.